This is section 11.8 on power series. So a power series is anything of this form here. All right. A power series centered at A is of the same form, only it's x minus A instead of just x. And a theorem that says that for a power series, there are only three possibilities. A series can converge when x is equal to A, that is, when this is 0, or the series converges for all x, or the third possibility is that there's a positive number r such that the series will converge when x minus a is less than r and diverges when x minus a is greater than r. So they give us a few examples, 1, 2, 3, 4 examples. They give you the corresponding radii of convergence and their corresponding interval of convergence. So we'll show you how to do this. It's essentially all you have to do is the ratio test. So let's show you how they get the radius of convergence and also the interval of convergence, which is what you'll have to do for these problems. So here it is. Find the radius of convergence and the interval of convergence of the given series. So like we mentioned, we're going to have to apply the ratio test, which says that the limit as n approaches as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, that's when it converges, right? That's what the ratio test says. So we have to apply the ratio theorem here, or the ratio test here. So if you do that, we're going to get the limit as n approaches infinity, absolute value, -1 n plus 1 x n plus 1 over cube root n plus 1 divided by a sub n, which means just multiply by the reciprocal. Okay, so notice that these are similar. They're going to cancel out, and you're going to be left with an x to the -1 because -1 to the 1 is -1. But then the absolute value of -1 becomes +1. So these essentially just cancel out. Okay. These both have cube roots, so we can combine those into 1. Same thing with these two terms. This will cancel out with this, but then you're going to be left with an x to the first power. So we're going to be left with limit as n approaches infinity of absolute value of x. That's from the x to the 1, because the x to the n's canceled, and you're left with x to the 1, which is this one. All right, and then times, we're going to be left with n over n plus 1 all to the cube root. I just combined the two cube roots into one single cube root, which you can do. All right, and this can be rewritten as (1 over 1 plus 1 over n). If you divide by n, divide by n, divide by n. And this, as n approaches infinity, this term will go to 0, so you're just going to get 1. But 1 times absolute value of x is going to be absolute value of x. So we know that this is converges when the absolute value of x is less than 1. That's the ratio test. That's what that ratio test tells us. All right, so in this case, that means that the radius of convergence is 1, because whatever number this is, that's your radius of convergence. So the interval of convergence will have to be, well, this inequality can be written as x is less than 1 or greater than -1, which means we still have to check the two endpoints. So let's check the two endpoints. In order to check the two endpoints, we got to plug in -1 and also +1. So let's plug in -1 for x into the original problem. So if you look at the original problem and you plug in -1 for x, you're going to get the series -1 to the n, -1 to the n, cube root of n. Over here, if you plug in +1 for x, you're going to get -1 to the n, 1 to the n, which is 1 to the n is just 1. over cube root of n. All right, this one here, when you add these two exponents, you're going to get 2n, and then the 2n makes this positive 1. So this just becomes 1 over cube root of n. And that's a p-series, and the p-series is going to diverge. Because p is 1/3, which is less than 1, so that makes it divergent. All right, because it's less than or equal to 1, I should say. All right, and then for the other endpoint at 1, that one is an alternating series test, and as you can see, these a sub n or b sub n is decreasing, so that means we can apply the alternating series test, and because the limit as n approaches infinity of 1 over n cubed is equal to 0, that means that this is convergent by the alternating series test. Therefore, it's divergent at -1, so it's not convergent. It's not part of the interval. It's exclusive on the left end, and on the right end, it is inclusive because it is convergent. So that is your interval of convergence. Here's your radius of convergence. All right, so that's the final answer. Let's move on to the next example. Okay, for the next one, it says it's the same direction. So let's go ahead and apply the ratio test again. All right, there's a ratio test. All right, so these two terms are going to cancel, and you're going to be left with the 2 to the first power. So I'm going to just cancel these out. And then the 2 to the first power, the absolute value of 2 is 2. So the 2, I'm just going to bring it out to the front of the limit since it's a constant. Okay, we still have absolute value of, these two terms are going to cancel, and you're going to be left with an x to the 1. So that's just going to be absolute value of x. And now we have these two, so let me cross those out. And now we just have these two left, which we can write as a single fraction raised to the second power. All right, and notice I didn't keep the absolute value around these because n's positive, so we don't need absolute value for positive numbers. So this is going to become, if you divide this by n, and n, you're going to get 1 plus 1 over n over 1 squared. This will approach 0 as n approaches infinity. And that's going to do it. So you're going to get 1 times 2. So you're going to end up with 2 absolute value of x. So that is that converges when it's less than 1 by the ratio test. All right, which means we can divide both sides by 2 and get the absolute value of x is less than 1/2. All right, so that is our radius of convergence. R equals 1/2. All right, so that's the radius of convergence. Now we have to check the endpoints, which means we have to write this in using the definition. We can write that as -1/2 on the left, +1/2 on the right. So the endpoints we have to check are -1/2 and +1/2. So let's check -1/2 first. So if you plug in -1/2 in for x here, you're going to get all right, notice that these two will cancel, but you're going to be left with the -1 to the n. So let's write that. All right, so you have -1 to the n squared, The test for divergence is going to tell us that this is going to go to infinity since the limit doesn't exist. So this is going to diverge, be divergent by test for divergence. All right, and let's check x equals positive 1/2 over here. So if you plug in positive 1/2 in for x, you're going to get 2 to the n squared 1/2 to the n. These cancel out, and you're just left with the series of n squared, which is also divergent by test for divergence, because the test for divergence says that if this limit does not equal 0, then it's divergent. So this limit clearly does not equal 0. So there we have our interval of convergence is going to be, they're divergent on both ends. So that means that our interval of convergence is going to be negative 1/2, comma, positive 1/2, open parentheses on both sides. All right. Let's try the next problem. All right, this one looks a little bit more complicated. This one's centered around 1, as you can see by this. All right, but we can still apply the same rule, or the same test, I should say, the ratio test. So that's going to be negative 1, n plus 1, x minus 1, n plus 1, 2, n plus 1 minus 1, 2, n plus 1 times the reciprocal. Absolute value. All right, so a lot of stuff is going to cancel. These two terms are going to cancel. You're going to be left with negative 1 to the 1, but the absolute value of negative 1 is positive 1, so that just disappears. These two will cancel. You'll be left with a 1/2, because you can be left with 2 to the 1 in the denominator, which is 1/2. I will write that out here, outside. Let's see, if we distribute here and here and subtract 1, simplify that, that's going to be 2n plus 2 minus 1 is 2n plus 1. So I'm just going to cancel that out and rewrite the simplified version. So this divided by this, and then these two terms are going to cancel. And you're going to be left with x minus 1 to the first. So our new limit becomes 1/2 limit n approaches infinity of absolute value of x minus 1. And then you have the whole 2n minus 1 over 2n plus 1. Okay. And that can be rewritten as 2 minus 1 over n, 2 plus 1 over n, and these terms go to 0. And 2 divided by 2 is 1, so that clearly is just equal to 1/2 absolute value of x minus 1. And that converges when 1/2 absolute value of x minus 1 is less than 1 by the ratio test, which implies that you can multiply both sides of the equation or inequality by 2. And there we go. We end up with this inequality, which tells us our radius of convergence is 2. And now we got to find the interval of convergence, which means we need to check the two endpoints. We have to rewrite this inequality as x minus 1 less than 2 greater than negative 2. If you add 1 to both sides, you're going to get negative 1 x 3. So these are the endpoints that we need to check, negative 1 and positive 3. Let's check them up here where there's more room. So I'm going to check x equals negative 1 first. Whoops. All right, if you plug in negative 1 in for x, that would be here. It's going to be negative 2 to the n. So we're going to have Okay, so notice that these two terms will cancel, but then you'll be left with the negative 1 to the n. But then you already have a negative 1 to the n, so those two negative 1 to the n's will just go away. So these three things we're going to cancel each other out. And so you'll just be left with 1 over 2n minus 1. And there's a couple tests you can perform. You can do the limit comparison test. You can do the integral test. If you do either test that you do, you're going to get that it's divergent. So for this one, since I'm out of space, you can do the integral test. You're going to get divergent by integral test. I'll leave that for you guys to verify. All right, and now let's check the other endpoint, which is 3. All right, so if you plug in 3, you're going to get the series of negative 1. 3 minus 1 is 2 to the n. 2n minus 1, 2 to the n. So here you have straight cancellation, and now you have that negative 1 to the n here. So you have the negative 1 to the n. So this is an alternating series test because the terms are decreasing, and clearly the limit of this is going to be 0. So this is going to converge by alternating series test. So one endpoint is going to, so the interval of convergence, on the left the negative 1 was divergent, so it's open parentheses. On the right, 3 was convergent, so close parentheses. And that is your interval of convergence. All right, I think there's one more problem. Yes, one more problem to go. All right, as you can see, this is a little strange. We can rewrite this as, let me rewrite it over here. Well, notice that there's a bunch of 2's that you can factor out. You can factor out a 2 from here, from here, from here, from here. So you can factor out a bunch of 2's from the denominator. So it turns out that this is the first, second, third, nth 2. So you're factoring n 2's out. And then you're just going to be left with 1 times 2 times 3 times ... times n, which is n factorial. So you're going to be left with that. All right. So this becomes this. I factored out 2, by the way, from here. Oh, 2 to the n, because there's 1, 2, 3, ... n 2's that I factored out. That's where this came from. Then this can be canceled with this. I'm going to rewrite this factorial as just n times n minus 1 factorial, so that I can simplify this n with this one. So now this can be rewritten as nx to the n 2 to the n minus 1 factorial. All right, this is where we're going to do the ratio test finally. So if you do the ratio test, you're going to get n plus 1, x to the n plus 1, 2 to the n plus 1, n plus 1 minus 1 is just n factorial, times the reciprocal. There we go. So once again, a lot of cancellation. This is going to cancel with, well, let me show you what's happening here. This can be rewritten as n times n minus 1 factorial. Then you can cancel these out. All right, these cancel, and you're left with the 2 in the denominator, which I'll write outside. And then these cancel, and you'll be left with an x to the first power in absolute value. So this becomes, and you still have n plus 1 over n squared because of the 2 n's here. All right, and if you divide the numerator and the denominator by the highest power of the denominator, which is n squared, you're going to end up with 1 over n plus 1 over n squared over 1, 0, 0. So this limit is going to approach 0. So when that happens, notice that we don't get a finite number. Notice that we get 0. So this means that it converges for all x. So we're going to say this is going to be by the ratio test. The series converges for all real x. That is, the radius of convergence is infinity. The interval of convergence is equal to negative infinity, positive infinity. So whenever you get your limit to equal to 0, then automatically by the ratio test, the series converges for all real x, and your radius of convergence is infinity, and your interval of convergence is negative infinity to positive infinity, and that is all.